This is a typical example involving the radial and transverse coordinate system, and it actually represents a double collar around a circular path. So we have rod OA, which rotates counterclockwise with a constant angular velocity of theta dot is equal to 5 radians per second. The double collar B is pin connected together such that one collar slides over the rotating rod and the other slides over the horizontal curved rod, of which the shape is described by the equation R is equal to 1.5 times 2 minus cosine theta. If both collars weighed together is 0.75 pound, determine the normal force which the curved rod exerts on one collar at the instant theta is equal to 120 degrees. We're also asked to neglect friction, so we do not have to worry about that. I would like to add another hint to be able to solve the problem more easily. Assume the normal force makes an angle of alpha equals to 19.11 degrees with the R axis. So if you take the normal reaction due to the circular shaft onto the collar and the R axis, the radial axis, there's an angle alpha equals to 19 between them. So I'll give you a couple of minutes to try to solve the problem. Remember, we're dealing with the radial and transverse components, so you need to make use of the kinematic equations related to that coordinate system. Once you are ready to check out the solution, simply continue the video. In step 1, we need to write down what we know. Well, there are lots of terms we need to write down. So theta dot is equal to 5 radians per second, that's given. We have an expression of R as a function of theta, 1.5 times 2 minus cosine theta. We have W is equal to 0.75 pound, that's the weight of the collar, and theta equals to 120 degrees. We also know that we do not have to worry about friction. And the actual variable we're looking for is N, the normal reaction force. What can we conclude from the problem statement? First, obviously, we need to deal with the radial and transversal coordinate system, since we're given an expression of R as a function of theta. Now, given this expression, we know which method we need to make use of in terms of kinematic equations. And so that actually refers to method 2 that we have seen at the end of chapter 12. So if we want to sketch the timeline or the different steps we need to follow to solve the problem, first we are given R as a function of theta. We can use method 2 and the kinematic equations to find AR and A theta. Once we know the acceleration components, we can make use of the kinetics or Newton's second law to link that to the forces and then solve for N. So that's the path we're going to follow. Step 2, as we have already done before for previous problem, involves drawing the free body diagram. We need to sketch the axes. So R is radially outwards, so we start from the center and intersect the collar at the position 120 degrees. And R is oriented outwards, as I've said. Theta is found by applying the right-hand rule and sketching the theta axis to be perpendicular to the R axis. Now that we have sketched both axes, we can write down the different forces. One important thing to keep in mind is since the shaft is not completely circular, so it's not an actual circle, and R follows a given expression, we cannot expect N to be completely aligned with R. Had it been an actual circle, N will definitely be collinear with the R axis. But in this case, since we have a random shape which follows a random equation, we cannot assume that. And so N was sketched to take a random direction. We are given from the hint that an angle alpha equals to 19.11 degrees is formed between the R axis and N, so we can make use of that to sketch N onto the diagram. Now, eventually we also have another force which is actually moving the collar, and so this force is labeled FOA, and it's actually generated by the fact that the linear rod is rotating at a specific rate. So two forces are acting onto the color. Now some of you might be wondering why n is directed downwards and not upwards. Well, the reason why I have labeled n in such a way is by simply thinking of the collar, which is rotating. I do expect the collar to hit the upper side of the shaft and not the lower side. And so the reaction force from the shaft would push the collar back inward for it not to slide out of the mechanism. If you still can't picture how the double collar works, I'll spend a couple of minutes explaining that. So the double collar is actually formed of two different components which are pinned together. One is allowed to slide along the shaft, the linear shaft, and the other one is allowed to slide along the circular shaft. But these two motions are actually dependent on one another since the two collars are pinned. So you cannot simply move along one of the rods without moving along the other. And so that's something you should keep in mind. So the motion is constrained for both. It's true that it can slide on both shafts, but it can do that only at the same time. There is only one specific path the collar can follow. We can move forward and write down step 3, which involves drawing the kinematic diagram. Again, we make use of the same axes, theta and r. We give a positive a for both of the components, assuming the coordinate system we have at hand. So MAR is directed outwards, positive direction. MA theta is directed towards the left, positive direction as well. Next, as we have discussed in chapter 12, whenever we're given r as a function of theta, we need to write the kinematic equations regarding the radial and transverse coordinate system, and that actually involves finding r dot and r double dot using method 2. So if you do not remember what method 2 is, method 2 involves using the chain rule for the expression of r as theta in order to derive r dot and r double dot. Now I know it's a complicated derivation, but you need to get used to it in order to solve any dynamic problem. So let us start off with the standard equation. R is equal to 1.5 times 2 minus cosine theta. In order to get r dot, which is equal to dr over dt, we need to take the derivative of that expression with respect to time. Now notice the expression is in terms of theta and we're taking the derivative with respect to time. So we obviously need to make use of the chain rule. And so applying the chain rule, one has the derivative of the expression with respect to theta times d theta over dt. Again, you can notice that we've added d theta in the numerator and the denominator. Now separating the two terms together, we have d theta over dt is equal to theta dot. And now we need to take the derivative of the expression of r, 3 minus 1.5 cosine theta. We derive that with respect to theta and we end up with a value 1.5 sine theta. That's for the first term. The second term remains as is, theta dot. And so this is the expression of r dot in terms of theta and theta dot. We were able to apply the chain rule once to get an expression of r dot. If we want to get the actual value of r dot at the specific instant theta is equal to 120, we simply need to replace theta by 120 and theta dot by 5. And so we'll end up with r dot is equal to 6.495 feet per second. But that's not the end of the story. We have calculated r dot. We still need to calculate r double dot. So r double dot is equal to d2r over dt2. Splitting up the two derivatives, we have d over dt of dr over dt. Now we can simply replace dr over dt with the expression we have found above. Remember, you make use of the expression as is in terms of the variables theta and its derivatives. You should not replace the expression with the final value we had for the specific instant. So you should not replace dr over dt by 6.495. This is wrong. So if we replace that with the general expression, 1.5 sine theta theta dot, derived with respect to time. Again, you notice here that we have an expression as a function of theta and its derivatives, and we need to find the derivative of that expression with respect to time. So it makes sense to make use of the chain rule again. So applying the chain rule, we have d of 1.5 sine theta theta dot divided by d theta times d theta over dt. Now looking at the second term, d theta over dt can be replaced by theta dot. The first term is the derivative of a product of two components. We have u is equal to 1.5 sine theta and v is equal to theta dot. And if you remember from calculus, the derivative of a product is u prime v plus v prime u. So let us find the derivative for the first term. Applying the equation from calculus, one has 1.5 cosine theta, that's u prime, times v, which is theta dot, plus 1.5 sine theta, which is u, times v prime, which is theta double dot. We then factor that with the second term, which is theta dot. Now expanding this expression, one has 1.5 cosine theta, theta dot squared, plus 1.5 sine theta, theta double dot, times theta dot. Now we still didn't find an expression for theta double dot, noting that theta dot is equal to 5, its derivative is equal to 0, since theta dot is a constant. And since theta double dot is equal to 0, we can get rid of the second term, which cancels out, and we're left out with the first term, which is 1.5 cosine theta, theta dot squared. So that's the expression of r double dot. If we want to get the value of r double dot at the specific instant, we simply need to replace theta and theta dot with their values, and we end up with r double dot is equal to minus 18.75 feet per second squared. I know it's a complicated derivation, but if you were not able to do that on your own, I highly recommend you to go back and try to solve this step on your own. And once you get used to it, you can move forward and look at the final solution. So now that we have solved the kinematic equations, we have r dot, r double dot, theta dot, and theta double dot. We can now calculate ar and a theta using kinematics. So looking at the formula sheet that you have at the end of your book, ar is equal to r double dot minus r theta dot squared. And replacing all the different terms we now have, ar is equal to minus 112.5 feet per second squared. We can do exactly the same for a theta. Plugging in the variable in its expression, we end up with a theta equal to 64.95 feet per second squared. So that's great. Now we have the acceleration. We can move forward. Remember, the next step is to find the forces from the acceleration. And to do so, we need to make use of the equations of motion, or the second law equation. Since we're dealing with a two-dimensional space, we can write two equations of motion. Sigma fr is equal to mar, and sigma f theta is equal to ma theta. Summing up the different forces acting on the radial direction, we have the projection of n minus n cosine 19.11 is equal to m times ar. Remember, since we're dealing again with the English units, we need to divide the weight by 32.2 to get the mass. And since we're dealing with a single unknown here, we can easily solve for n. N is equal to 2.77 pound. Now from the second equation, one has FOA plus 277 sine 19.11 is equal to m times a theta. One can solve for FOA as well, and we end up with a value of 0.605 pounds. So this is all for this problem. Now I have added this hint onto the original problem just to help you out. I would like to spare a couple of minutes to discuss how can one obtain the value of alpha, which we have said is equal to 19.11, on his own. So how to find the angle the normal force makes with the r-axis? One needs to remember a couple of things. First, the angle between two parametric lines can be found by applying tan phi. Let's say the angle between the two lines is equal to the first function, which is parametric, divided by the second function, which is also parametric. And so once you apply trigonometry and get phi, you can evaluate phi for any value theta might take, and you'll find the solution of phi. So let us apply that in practice. Let xi be the angle between the r-axis and the tangent to the circular path. So the tangent to the circular path is simply the t-axis. If we want to find the angle between them, as you can see in the schematic, we can write tan xi is equal to r, the equation of r, divided by the equation of the tangent, which is dr divided by d theta. Now replacing r with its expression and dr over d theta with its own expression, we get the following. Remember to get xi, you need to replace theta with 120 degrees, and so you end up with xi is equal to 70.89 degrees. But that's not all. Remember, the angle alpha is between n and the r-axis. So we still need to apply some trigonometry in order to find the angle alpha. Now looking at the schematic I have drawn, notice that n is perpendicular to the tangent axis. And so to find the angle alpha between n and r, you simply need to perform 90 minus xi, which gives us again 19.11 degrees. If some of you were wondering why the normal is perpendicular to the tangent axis, well, remember the reaction force, N, is always perpendicular to the surface. When the surface is flat, N is perpendicular to that surface, but when we're dealing with the circular path, N is perpendicular to the tangent of that surface. And so the tangent of the surface at that specific point is the t-axis. And that's why N and the t-axis form an angle of 90 degrees. So in summary, always keep in mind that the angle between two parametric lines can be found by the expression tan xi is equal to f1 over f2 evaluated at a specific theta. This is a standard problem you might encounter in your exam, so I highly recommend you practice this problem again and again until you get used to it.